Unlike solving linear programming problems with graphs and geometrically, when we're doing the simplex method, there is a big difference in how we approach a minimization problem and a maximization problem. And a lot of the difference is in the setup and in how we interpret the result. So today what we're going to do is we're going to minimize with the simplex method. The process in the middle is still exactly the same, which is nice. The difference is in the setup and the interpretation of the result. So first let's look at how the setup is different. To do that, we're going to introduce the idea of a dual problem. The idea behind a dual problem is that every minimization problem has a corresponding maximization problem. And similarly, every maximization problem has a corresponding minimization problem. The best example of this is if you look at a rectangular box. And if you want to maximize the area inside the box while you minimize, I'll just say min, we can minimize the surface area. So, I shouldn't say maximize area, I should say maximize volume. Maximize the volume inside the box, minimize the surface area of the box. Both of these are the same problem as you work them out. And it turns out both of these, the solution is a cube. A cube has the most volume for the minimum surface area. Every maximization problem has a minimization problem that has the exact same solution. Every minimization problem has a maximization problem that has the exact same solution. And since the simplex method is used for maximization, what we will do is we will convert the minimization problem into a maximization problem. And the way we make that conversion is a simple process. First, we will create a matrix for each inequality. And we'll also include the objective function in here with z equals 0. So we're not moving things around, we're not adding slack variables. These are just the inequalities and the objective function as a matrix. And then what we're going to do is what is called transpose the matrix. What that means is we are going to switch the rows and the columns. So the rows will become columns and the columns will become rows. And once we have that new transpose matrix, we will write new inequalities and new objective function. And this will represent the problem that wants to be maximized. That will have the same solution as the corresponding minimization problem. These are called duals. Both seem like two different problems, but both have the exact same solution. One's a maximum, one's a minimum, but it's the same solution at the same point for both problems. So, for example, to kind of set that up, let's look at just a simple problem. Let's say a plus 2b is greater than or equal to 17. 3a plus 6b is greater than or equal to 12. And z equals 5a plus 4b. That's our inequality. This is what we want to minimize. Now, what we're going to do is we're going to convert this into a matrix. So we've got 1a, 2b, and 17. We've got 3a, 6b, and 12. Then we've got 5a, 4b, and we make z equal to 0. So this matrix represents what we are trying to maximize. When we transpose it, the rows become columns and the columns become rows. So this first column, 1, 3, 5, becomes row 1. 1, 3, 5. The second column becomes row 2. 2, 6, 4. And the third column becomes row 3. 17, 12, 0. This then we can convert to our inequalities. Before, when our inequality had before when our matrix had columns for a, b, and the constants, now the columns represent what we used to call our slack variables, y1, y2, and the constants. So we've got y1 plus 3y2 is less than or equal to 5. 2y1 plus 6y2 is less than or equal to 4. And then our z is equal to 17y1 plus 12y2. And then we would have our dual problem. Both this problem, which used the slack variables that we're trying to maximize, and this other problem, which use our actual variables that we're trying to minimize, have the exact same solution point. One of them has a maximum, one of them has a minimum, but it's the same value both directions. And we can solve the second one using the simplex method. We're not going to do that here, though. We're going to actually jump to solving some real problems. So we're going to actually now minimize with the simplex method, which really means find the dual and maximize. Because the simplex method can only maximize. So we will maximize the dual, which has the exact same solution as the minimize problem. So once it's set up, we will solve it just like the maximization process that we saw yesterday. However, the solution, I told you we have to interpret the solution differently. The solution is the slack variables in the last column of the dual. Let me show you what I mean by that with an example problem. Let's say an oil company has 2 refineries. The first cost $20,000 per day to operate, and it produces 400 barrels of high-grade oil, 300 barrels of medium grade, and 200 barrels of low-grade oil. Each day. A little more space. The second costs $25,000 per day and produces 300 barrels of high grade, 400 barrels of medium, and 500 barrels of low-grade oil daily. There is an order for 25,000 barrels of high grade, 27,000 barrels of medium, and 30,000 barrels of low grade. How many of each? Actually, I should say how many days should each refinery be used to minimize cost? Well, let's take a look at our constraints. What we are constrained by is we need so much of the high grade, medium grade, and low grade. And what we want to do is we want to minimize the cost, if I can get that all on one screen. So looking at the high grade, we'll call the first refinery Refinery A. And the second refinery I'll call Refinery B. So we'll have variables A and B. The first, looking at high grade, the first one produces 400 barrels of high grade. The second one produces 300 barrels of high grade. And we need 25,000 barrels of high grade. So we've got 400 of from the first, from Refinery A, and 300 from Refinery B, has to be greater than or equal to 25,000. We say greater than or equal to is because if we make extra oil, that's okay, but we need at least this much to satisfy the purchase request. Similarly, with the medium grade, refinery A has 300, B has 400, and we need at least 27,000. So 300 from A plus 400 from B has to be greater than or equal to the 27,000. With the low grade, we need 200 barrels from A and 500 barrels from B with a minimum of 30,000. So 500 from A plus, it's 300 from A. 300 from A plus 500 from B have to give us at least greater than or equal to 30,000. Oops, I really can't read here. I'm looking at the third line here. It's 200 barrels of low grade from A, not 300. 200 low grade from A. There we go. And then for the cost function, the cost we get A is 20,000 a day and B costs 25,000 a day. That's what we're trying to minimize. Z is 20,000 for each A plus 25,000 for each day of B. We have our constraints and we have our objective function, but this is something we want to minimize. Simplex can't minimize. Simplex can only maximize. So what we're going to do is we're going to convert this into a matrix, transpose the matrix to get our dual problem. So first the matrix is 400 A's, 300 B's, and then for our constant 25,000. The medium is 300 A's plus 400 B's. The constant is 27,000. The low grade, we've got 200 from A, 500 from B, and then 30,000. And then what we're trying to maximize is 20,000, 25,000, and then Z is always equal to 0. And so when we transpose this matrix, our columns become row 1, row 2, and row 3. So the columns, we get 400, 300, 200, and 20,000. Then 300, 400, 500, and 25,000. Then we get 25,000, 27,000, 30,000, and 0. And then from this we create our dual inequalities, the dual that we're going to try and maximize using now slack variables y1, y2, y3, and our constants. So we've got 400 y1s plus 300 y2s plus 200 y3s, now less than or equal to 20,000. 300 y1s plus 400 y2s plus 500 y3s is less than or equal to 25,000. And then The last column represents our z, 25,000 plus 27,000 plus 30,000. Oops. y1, y2, and y3, of course. And now we have our dual. Both of these inequalities represent the same solution, the same problem. One is a minimization, one is a maximization, but both will have the same solution. So now we can use the simplex method. The simplex method says we're going to add a slack variable to each equation. Here's the catch. The slack variable that we add to the first inequality is the first variable from the original problem. The slack variable we're going to add is a to the first inequality. The second inequality is the second variable in the minimization problem. So we're going to add b. So that's how we get a and b back in our equation to make 400y1 plus 300y2 plus 200y3 plus a is equal now to the 20,000. 300y1 plus 400y2 plus 500y3 plus the second variable b is equal to 25,000. And z, when we subtract everything over to the other side and making it negative, we get negative 25,000 y1, negative 27,000 y2, negative 30,000 y3 plus z always equals 0. We're now ready to make our simplex table, tableau, matrix, whatever you want to call it. We'll have a column for y1, y2, y3, a, b, and z, and then our constants at the end. It's going to make a big matrix, but the process we know is exactly the same. 400, 300, 200, 1, 0, 0, 20,000. 300, 400, 500, 0, 1, 0, 25,000. Negative 25,000. Negative 27,000, negative 30,000, 0, 0, 1, 0. And again, I always like to check to make sure I set it up right. I should see what looks like the identity matrix in the middle. We do. We're good to move on to simplify by the simplex method. And the most negative entry is the negative 30,000. So we know our pivot column is y3. We need to find our rows, so we're going to divide the first row by 200. 20,000 divided by 200 is 100. 25,000 divided by 500 is 50. The smallest one there is the 50, so the pivot is in the second row, which means our pivot value is the 500. So we make that pivot value 1 by multiplying by the reciprocal 1 over 500 times row 2 to get the new row 2. And now again we'll bring back our calculator to help us out. Second matrix, go over to edit. This time we've got 3 rows and 7 columns again. Entering in the values of 400, 300, 200, 1, 0, 0, 20,000, 300, 400, 500, 0, 1, 0, 25,000, negative 25,000, negative 27,000, negative 30,000, 0, 0, 1, 0, second quit. And I like to put the matrix on the screen just so that I can look at it and make sure it's right. I've typed it in correctly, checking my values. 200, 500, negative 30,000, yep. $20,000, $25,000, and 0. Looks good. So now we're ready to take those matrix operations, second matrix, over to math. We're just multiplying to begin with. We're multiplying by 1 divided by 500, comma, the previous matrix in row 2. Didn't get the 2. There we go. And if we hit math to make everything a fraction, we get these values. So that matrix now is 400, 300, 200, 100, 20,000, 3/5, 4/5, 1, 0, 1 over 500, 0, 50, negative 25,000, negative 27,000, negative 30,000, 0, 0, 1, 0. Now that we've got that 1 on the pivot point, we're going to make the other values there 0. Let's make sure we keep our matrices separated to our augmented matrices so it looks like our tableau. There we go. And so we're going to use opposites. We're going to use negative 200 times row 2, add it to row 1 to get the new row 1. And positive 30,000 times row 3, we're going to add it, times row 2, that's where the pivot is. We'll add it to row 3 to get a new row 3. And when we do that, second matrix. We'll go over to do math, scroll up 1, we're going to multiply and add negative 200, comma, times the previous matrix in row 2, and we're going to add it to row 1. We should see a 0 now if we scroll over a bit. Yep, 0. So second matrix, do math, up, we're going to add and multiply, and we're also going to do 30,000 times the previous matrix in row 2, and we're going to add it to row 3. I don't see any decimals, so I think we're going to be okay. Some calculators may revert back to decimals instead of fractions, but we did not, so we're good to just copy this guy. We have 280, 3/5, and negative 7,000. Then we have 140, 4/5, and negative 3,000. And then we have the 0, 1, 0 that we just built. The 1, 0, 0 is going to be unchanged. Scrolling over, we have a negative 2/5, 1 over 500, and and then it was 60. Then we'll have 0, 0, 1, and finally 10,050 and 1.5 million. That's 5 zeros. 10,050 and 1.5 million. That's 5 zeros. And we've got our next step. We still have negatives in the bottom rows, so we still have work to do. Taking a look at the most negative entry, that's the negative 70,000. So we're going to divide by 280, and we're going to divide by 3/5. Again, make sure you do this on a different calculator. You don't want to lose the matrix in the previous answer. You're going to have to redo everything you've already done. When we divide by 280, just as a decimal, I'm getting 35.7. When I divide by 3/5 as a decimal, I'm getting 83.3. The decimal part doesn't matter too much. We just need to know that the first row and the first column give us the pivot at the 280 point. So we need to get rid of that 280 by multiplying by the reciprocal, 1 over 280 times row 1, to get our new row 1. So on the calculator, second matrix, over to do math, and up twice to get to multiplying. And we're going to do 1 over 280, comma, times the previous answer, comma, in row 1 only, close the parentheses, and we get some decimals, so I'll hit math fraction so that I can see. So that first row is 1, 1/2, 0. 1 over 280, negative 1 over 700, 0. And then finally it's 250 over 7. The other two rows are unchanged, so we've got 3/5, 3/5, 1, 0, 1 over 500, 0, 50, negative 7,000, negative 3,000, 0, 0, 61, and the 1.5 million. That's 5 zeros. We've got our pivot 1. We need to make the other entries into 1s as well. We do that by multiplying by opposites. So we've got negative 3/5 times row 1 plus row 2 will give us the new row 2. Positive 7,000 times row 1 plus row 3 will give us the new row 3. See if we have any negatives left in the bottom row after we do that. So second matrix. Over to math, we're going to multiply and add rows. We're going to do negative 3/5, comma, times the previous answer, comma, in row 1, comma, into row 2, close the parentheses, enter. Do it one more time, second matrix, over to math, up to multiply and add rows. We've got 7,000, comma, times the previous answer, comma, from row 1 to row 3, enter, and we'll make everything into fractions. So copying this matrix down, we got 1, 0, 0, 1/2, 1/2, 500. 1, 0, 0, 1/2, 1/2, 500. 0, 1, 0. 1 over 280, negative 3 over 1400, 25. 1 over 280, negative 3 over 1400, 25. I'll scroll over and see if we can get the rest of this matrix on the screen. I can. Negative 1 over 700, 1 over 350, and 50. Negative 1 over 700, 1 over 350, and 50. And then finally we have the 0, 0, 1. In the last column, 250 over 7, 200 over 7, and 1.75 million. That's 4 zeros. So we've got 250 over 7, 200 over 7, and then 1.75 million. And if you remember from the beginning, we said our columns were labeled y1, y2, y3, our slack variables first. Those are from the dual. The next columns are our A and B from the two options, the two refineries that the oil company is working with. Then our Z and our constants. The difference with minimization is the setup's different. It's a dual problem you've got to set up. The middle is the same. The end, how we interpret the final result, is also a little bit different. Our final result comes from the bottom row. The bottom row tells us the A variable is 25, the B variable is 50, and Z still works like before. So, as our final answer, refinery A should work for 25 days. Refinery B should work for 50 days. And Z, the minimum cost is going to be 1.75 million. That's 4 zeros to generate this order. Minimum cost, 25 days on the first refinery, 50 days on the second refinery. The way we solve then, just to summarize, the way we minimize with the simplex method is we find a dual problem. We find the dual by changing the matrix that represents the inequalities and the constraints, take the transpose to get the new system. Solve that new system just like before. The only difference now is the results are actually in the bottom row, and your slack variables are the variables that we were looking for. Good way to do this is practice, practice, practice. We'll see you tomorrow with questions. Good luck to you.